Do you guys remember anything about work?
Hold on, I have minutes.
If you don't get paid in slavery, it's like if you don't get paid in slavery.
Okay. Okay, so what work does is it changes the energy of a system. And it changes the energy of a system through some means of pushing or pulling. When you hear that, what do you think? Starts with an F. Force, okay? So here's the equation for work that we're about to derive. And we're deriving it because you guys have to know how to derive equations for the AP exam. So don't think like, oh, I've got the equation. I don't have to derive it. Stick with me, okay?
You have to show how to derive equations on the AP?
Every now and then, yeah. They didn't have to last year because it was all typed, but this year they're still planning on doing it like normal. And they usually have you derive stuff. So work is equal to force times distance, okay? So the W is work, the F is force, and the D is distance. Does anybody know what the units are for work?
Joules?
They are joules. Good job, Jacob. Joules, okay? Then we've got, so I'll write work above this though, so we know we did. Then we've got potential energy. Does anybody know what potential energy is? What defines potential energy? Like what's special about it? Potential energy is stored, okay? It's energy that's stored up, and it depends on the height of an object, okay? At least gravitational potential energy does. How we represent potential energy, how do you guys think we represent potential energy? What do you think we use as our variable?
P.
No.
K.
No.
Very simple.
Oh, no, P.
Q.
Okay. What do you think the unit is for potential energy?
Watts.
No.
Is it also joules?
It is also joules.
That's tough.
Okay, and like we said, this is associated with position / height. I'm not going to give you the equation for that yet. Don't worry, we'll get there. Okay? This is sort of just like an overview of everything we're about to be talking about, if that makes sense. The next thing is kinetic energy. How do you think we represent kinetic energy? Yeah, this one, thankfully, is just KE. What do you think the unit is for kinetic energy? It is also joules, yeah.
Crazy.
Now, if potential energy is associated with position and height, what do you think kinetic energy is associated with? Movement, right? It's associated with motion. So we've covered the work, we've covered the energy. Now on to power. How do you guys think we represent power?
Watts.
Well, I mean unit-wise.
Watts.
P, it's a P for power. The unit though, yes, Donald, is watts. Okay? The unit is watts. What is power?
Energy.
It has to do with energy.
The amount of energy to achieve a certain amount of work.
No, well, it has to do with work, but it has to do with something else too. It's the rate at which we do work. So it's how much time it takes to do work, okay? Or the rate at which energy is transferred, which would be, so rate at which energy is transferred / work is done. Okay, and you guys, spoiler alert, there's like 3 equations for work. This isn't the only one. Yeah, we're going to derive all of them. This is just the most basic one.
Do any of them involve angles?
Yes.
Wait, so forces equal mass times acceleration.
No.
Are you going to be doing that?
We're going to be talking about it, yeah.
Oh, part of the
I don't know if it's today or if it's when we get to impulse later on after this, but we get around to some cool stuff. Okay. Any questions about our little overview here? No? Okay. So one more thing, just to make sure we all know this. You guys, what's the law of conservation of energy?
Energy cannot be created or destroyed.
It can only be
It cannot be transferred.
transferred or transformed, okay? So don't forget that. Energy cannot be created or destroyed. It can only be transferred or transformed. So now with that little review from physical science, we can start talking a little bit more, okay? So when we talk about energy, we like to think about systems and environments, okay? And what's happening is that energy can get added, removed, and transferred throughout different systems and environments. So think about moving money between bank accounts. Do you guys have bank accounts?
Yeah.
You have like a checking and a savings?
Yeah.
No, if you don't have a savings, you should probably get one, okay?
Everything is saving.
But you move stuff around, don't you? Like, so every month, as soon as my husband gets paid, we actually move his entire paycheck into savings. We only live off of mine. Right? Okay? Huh? What if lights?
What if flex?
Oh, what a flex, yeah. Listen, it's something we agreed on before we got married. We were like, we're just going to live off of my paycheck. We're not going to use yours. We save it. So when you transfer something, have you ever looked at like the list on your checking account? What does it show up as? Does it show up as like a moved a positive or a negative? You guys ever look at that?
No.
No? Okay. So what happens is, let's say you've got your checking account and you got your savings. Okay? And you want to move $1,000 from checking to savings. If you brought up your banking app and you looked at all your transactions in checking, it would show negative 1,000. And then over in savings, it would show positive 1,000. Okay? And this is considered a negative deposit. And this is sort of how energy transfer works. You would lose it on one end, but then you end up gaining it in another place. Bless you, Jacob. Okay? So that's just a little thing I like to use every now and then to describe that, okay? So what happens then is if instead of money, we're transferring work, and we're transferring, that means like kinetic, potential energy, all that stuff. If we're transferring work, what happens is we say that the change in the energy of a system is equal to work external, and that's what we call the energy principle. Okay? And when we say work external, we just mean any work that's done by the outside environment. Okay?
Is it principle or principle?
Oh my God, I spelled it wrong. It's L-E. It's right in my notes, and then I put it wrong. Woo! Principle. Okay? So we're going to be using a basic energy model moving forward, okay, you guys? Let's say we've got a box. Okay? The box is considered our system, and everything outside of the box is considered the environment. Okay? Now, within the system, we have kinetic energy, potential energy, and we're also going to have thermal energy. Okay? And sometimes we'll have energy that's coming in, which means that the work being done is greater than 0, okay? But sometimes we also have energy.
What's the energy peak?
It's thermal energy. We don't do as much with thermal, but we still mention it because sometimes thermal energy, what do you guys think thermal energy is caused by that we use a lot?
Friction.
Friction, okay? And when we've got energy out, the work is actually going to be less than 0. And what happens within the system is that the energy is transforming from one thing to another. So this is just sort of just like a visual representation of sort of what's going on. We're not really going to worry about, you guys have probably heard about chemical and heat energies. We're not really worried about those right now. And yes, heat and thermal energy are 2 different things.
What?
They
Are there
are.
any classes there?
Is there like a thermal potential?
I don't think so.
So like, you know, like hot hands?
That's chemical, yeah.
Oh shoot, transferring it from chemical to heat.
Oh, all right. So this is sort of just a visual representation of what we're going to be talking about. Don't worry, all these pictures and more are actually already posted. So let's talk about work and kinetic energy, how they relate to a single particle. Okay, so we're focusing on one particle. So let's say we have a particle of mass m. Okay, so here's our particle. Mass is m. And it's going to get acted on by some force F. Okay, so this is our particle. It's getting acted on by a force. And it's going to act parallel to the direction of motion. So let's say maybe this is our force. Okay, it's moving to the left. A force acts to the left. Okay, so that means that work is being done on this particle. Because work, in order for work to be done, it has to be applying a force in the direction of motion. Does that make sense? For positive work to be done. What kind of work do you think would be done if it was moving to the left and then a friction came in? What kind of work would the friction be doing, positive or negative? It'd be doing negative work on the particle, right? Okay, does that make sense to everybody?
Yeah.
Yeah? Awesome. You guys are so smart. I'm getting to skip over some stuff. It's nice. I might get through this today. Yeah? Okay. And now we're going to look at what Donald mentioned about Newton's second law. Here's on that, okay? So what do we know is Newton's second law? Force is equal to mass times acceleration, right? And the subscript we're going to use throughout all of this, just to make it something new so we don't stress about it, is for everything that's a vector, we're going to put a little subscript of an S, okay? To show that it's going in the S direction, because vectors have to have direction, right?
What's the S for?
It's just an overall like direction that you can use. Like it could be positive, negative, it could be X, Y, whatever. It's just S. It's just like an arbitrary direction.
Alright.
It's saying there's some direction applied to it, okay? Now, isn't acceleration the derivative of velocity?
I suppose you could say that.
So this shows us how velocity changes with time, right? That's all acceleration is, correct? It shows us that velocity changes with time.
That's why they write derivative of signs like that.
Mm-hmm.
What?
The more you know. So see how velocity changes with respect to time? Awesome. So we want to know, though, how velocity changes with position. So are you guys familiar with the chain rule? Where you guys are like, oh God. Okay, so we're going to do some chain rule on acceleration, aka the derivative of velocity, okay? So we can see how it changes in relation to position. So what that would end up looking at is, remember, you guys, that our S is representing basically our position and our direction, right? Okay? So the derivative of velocity with respect to position times, yeah, that's what I told you guys, like it's our overall direction, right? You see how this is the same thing as this, right? Yeah? Everybody gets that? That this is the same thing? Because what would happen with these? What would they do?
Cancel.
They would cancel, right? However, if we multiply them together, we of course know that dvs over dt is still velocity, right? So, actually, hold on. And we know that ds over dt is what? What's position over time, you guys? Velocity. So that's velocity, right? So we can say that velocity times dvs ds. So all three of these things are the same. And that gives us, lets us see how velocity changes with position. You might be wondering, why did we do this? Well, we have to integrate some stuff, you guys. I'm sorry. Who likes integration? Woo! Integration. Okay. So let me show you the integral that we're starting with, okay? We have the integral from our initial velocity to our final velocity of m v dv is equal to the integral from our initial position to our final position of fs ds. And that's what we're going to be working with today.
That's because the FSDS is what's equal to acceleration.
Yeah.
Okay. Where does that come from?
We just showed it. We just derived it. Here, I can plug it back in. Okay. So you guys know how we started out with this?
Yes.
And then we ended up showing that this is this, right? That's what we just did with the chain rule?
Yeah.
Okay. So we take this, multiply both sides by it.
I was asking about the right side.
That is the right side.
Oh, this is the right side.
So we got the force and the distance together, and mass and the velocity together.
So why do we multiply both sides by yeah.
Because what I said back at the beginning, that we know that work is force times distance, and also this integration would be messy, and I don't want to do it. Where'd it go? There I am. Okay. So the side that we're going to start out with, though, is going to be this left side, okay? We're going to start out dealing with the left side. So if we're starting out with the left side, do you guys see anything that we can pull out that we're not going to have to deal with?
Yes.
Not quiet, because VS, DVS, this is sort of what's basically going to have to get integrated together. So what about the mass? Can we take out the mass? No, you just bring it to the outside. You guys, we're only dealing with the left side right now. That's what I said. We're focusing on the left side. We're going to do the right side later. You guys have made it to integrals and calculus by now, haven't you?
No.
What the heck?
We all just failed the test on this.
Yeah, it was not good.
What'd you get?
I don't think I failed.
What'd you get? Yesterday was
Okay, well, we can pull out the m, you guys, because the m is a constant here, okay? Our mass isn't changing. What has the potential to change is velocity, not mass, all right? Because the VS, DVS is what tells us that velocity is changing. This right here says, oh, velocity is going to change, okay? So that has to stay within the integral because it's what we're concerned with changing. The mass, though, it's constant. We don't have to worry about it, okay? We're not concerned. If it started out as 5, it's going to end as 5, okay? Does that make sense? Yeah? Okay. It's also nice to know that I'm not the only AP teacher behind. Alrighty. So, we still have mass on the outside, right? Now, do you guys remember anything about when I taught you how to integrate at the beginning of the year?
No.
Do you have your notes?
I don't know. So, why is it on the right side?
Just probably a bunch of lines. Because it's carrying over to
We're doing the integration part now. So now we're going to integrate this. So this is like the next step.
Well, I remember it is in you add 1 to the exponent and then divide by that exponent.
Oh.
No, you divide by the exponent. So you add 1, you take that.
No, what you say is that like the existing exponent is you add it.
Trying to see when I taught you guys how to integrate.
That is exactly what he's saying.
No, I know.
Here, I'll write it back up for you guys so you guys can put it back in your notes, okay? Hey, you guys, I'm going to write up the formula for integration so we can all put it in our notes, okay?
Awesome.
Awesome. Okay, so
Apparently, I think we'll be on the FAQ. That's when I said
So we'll just use time as an example. If we're integrating from initial to final, we've got some constant. And then we've got our variable that's showing change, right? What happens is you end up with ct to the n plus 1 over n plus 1. And it goes from whatever your initial constraint is to your final one. And then from there, you end up with that.
What? Oh. Okay,
That's the formula for integration.
Where's the constant?
No, it's from a coefficient.
The constant's the c.
Did you add that?
No, it's part of the thing. It's part of it's like it's combined. So like this m is just going to get back multiplied in like it started. But we just take it out so we don't worry about integrating it because it doesn't need to be integrated. It's a constant. So let me show you how it happens with this one, okay? So if we're taking the integral of this, what is, so the Vs here is the T here, right? That's what it represents? Okay, so what do we do with it? What would be this form? The constant's already on the outside, so you don't have to worry about it. It's already out here, like off to the side. It's like it's over here. So what's going to be on our top? What's going to be our Tn plus 1? What will it be? Over what?
2.
Okay. And that's going to get evaluated from our initial velocity to our final velocity.
So, do we do the thing in this class where you don't know the position where it is on the, like, you don't know the starting position, so you add a imaginary constant?
That's an indefinite integral. This is a definite integral. Because we have defined borders that we're integrating across. So it's a defined integral. We don't do indefinite integrals. How do you guys know what an indefinite integral is if you haven't done integrals yet?
That's how you get the position function from acceleration. It's an indefinite integral.
You can do that with a definite integral.
Well, we wouldn't get the initial.
When we did it at the beginning of the year, we used definite integrals.
But you
Anyways.
still add the constant.
Okay, so now we need to keep moving. Okay, so that means we're going to have VFS squared over 2 minus VF naught squared over 2. And don't forget that we've got the M over here on the outside to still get distributed. So then we can distribute the M. And is there a way that we can write this other than like this? Couldn't we say 1/2 VFS squared? You guys, isn't that the same thing? Yeah, and then it's getting multiplied by M.
Oh, okay. So it still does have C, but since you're subtracting, since the first term and the second term from the ranges, you can add C to those, and that's the proper notation. But it just gets subtracted away since both the terms have C, and they get subtracted away. So that's why it doesn't matter with definite integrals.
Sure.
So say that 1/2 VF squared M has a plus C, and that's a term. And then the next one, the minus 1/2 VO squared M, has plus C. And then that's what the resultant of an integral is. And since they get subtracted, it doesn't matter.
Yes.
Oh, because you're saying because the negative gets distributed to the
negative,
plus C.
It gets rid of it. So that's why I was confused about why there wasn't a C.
I'm just confused with how much integration practice we did and you guys can't remember anything. Okay, so if we have a final minus an initial, don't we usually consider that a change in something?
Yeah.
Yeah. So it's a change in 1/2 MV squared. Okay. We call this a change in kinetic energy, which is one of the equations for work.
Wait, so we have to derive that if you're Yeah, you can't just use like.
Well, that makes sense.
Only if they tell you you have to derive it. They might not tell you have to derive it.
Okay.
But I showed you how to derive it. So if you have to derive it, you've derived it. Okay? So this means that our equation for kinetic energy is 1/2 mv squared. Okay? And you guys should notice that I dropped the s. Remember how I said the s is what made it a vector? Well, once you square it, it really doesn't matter the direction anymore because the direction sort of goes away when you square something. So that's why when we just put it together as a change in, you can drop the s for the vector because it's not a vector anymore. Kinetic energy is not a vector because the only vector quantity gets squared. So like if it's a negative, what's going to happen?
What is that?
It's gonna become positive.
Become positive. If it's a positive, what happens? What'd you ask, Donald?
Are the other energies a vector?
No. None of the energies are vectors.
So where's the vector used?
The vector's used in the derivation. Because like, for instance, if you were doing the change in here like normal, right?
You wouldn't get the ds.
It just ends up not mattering when it's squared.
Okay.
The direction goes away when you square something. Okay. So if a particle speeds up, the kinetic energy, do you think it's going to be positive or negative? The change in kinetic energy.
Negative?
If it speeds up,
Positive.
Oh.
yeah, the particle speeds up, the kinetic energy is going to be positive because it's final minus initial. So if the final speed's faster than the initial speed, it means we're going to have a positive result. Now, what if the particle slows down? What will the change in kinetic energy be? Will it be positive, negative, or zero? It's going to be negative. I mean, it could be zero. You never know, but no, not really. It has to stay the same, right? So if it's positive, that means it's had a gain. A gin, really? It's had a gain in kinetic energy. And if it's negative, it has lost kinetic energy. Now remember that this is changing, okay? You see the deltas? So can kinetic energy itself ever be negative? No. If you get a negative, just kinetic energy on its own, not a change in, you've done something super wrong, okay? Why can it never be negative?
Because that's implying that you're
What's the equation?
losing.
1/2 mv squared. None of those values can end.
None of these can be negative. None of these can be negative, okay? So you should never have a negative kinetic energy. You can have a negative change in, but not just a negative kinetic energy. So let's see here. If we have a car that weighs, well, has a mass of about 1,000 kilograms, and it's going a speed of 20 meters per second. And then we've got another car that's 2,000 kilograms. And it's going a speed of 10 meters per second. Which one has more kinetic energy? You can do the math. Take out your calculator. 1/2. 10,000.
That's because 20 squared.
Yeah, you're so smart. 20 squared is going to give you a much bigger number than 10 squared, isn't it? So this one would have more kinetic energy. Okay, so we just derived kinetic energy equation, that one. That was the left side, right, of the integral. So now we're going to go on to the right side of the integral. Okay, so the right-hand side of the integral is going to be what tells us how much kinetic energy changes due to a force. Remember, because we had the force on the right side, right, you guys? And the left side showed us kinetic energy change, so the right side is going to show us how much that kinetic energy changes due to a force, okay? So, the right side was the integral from some initial position to some final position of Fs ds. Okay? What can we take out of the integral as a constant?
Yes.
The force, right? We'll take the force out. So we have the force on the outside as a constant. And what we're integrating is the position, right? So that's why you see how it's ds, so it's a position. Yeah? So we're not integrating force, we're integrating position, correct? So that's why the force can come out and the position has to stay in. Okay? So do you guys remember what just this would become in integration? If you just have a ds or a dv or a dt and there's nothing else with it, it just becomes an s. So if you ever have an integral like this, no matter what it is, even if it's dv, this would just become an s. This would just become a v, and so on and so forth. Okay, you guys? And we're integrating from the initial to the final. So that means that we would have the force times the final position minus the force times the initial position, right?
This is a dumb question. But why is the force constant?
Okay, so why we consider the force to be constant here is because with this integration right here, right? What's changing is position. That's what the ds tells us. It tells us that only the position is changing, which means the force isn't considered to be changing within this integral, or else it would be df.
What's df?
Well, that would say the force is changing. Yeah,
Okay, so if it has a derivative on it.
that's what's changing.
Okay,
Mhm.
and since we're taking the integral derivative, it just cancels out the derivative.
Yeah, so the force comes out. Then we take the integral of the derivative, which an integral of the derivative is just its original function.
Yeah.
And then we get this, which tells us that it is going to be force times a change in distance. And do you notice that this time we kept the direction on the force? Yeah, because force is still going to be a vector in this situation. It wasn't squared, which means direction still matters. And this is that basically that FD that I showed you at the beginning, the force times the distance. That's what this is.
Okay. It makes sense as to why it needs like position. I mean, like the integral.
Mm-hmm. So that means that if you guys were given a graph, that work is the area under the curve of a force versus position graph. And that's where we're going to stop today because my alarm went off to let me know there was only 3 minutes left in class like a minute ago. Yeah, the bell's going to ring in about a minute.